there. If you do have any questions whilst I'm talking, do pop them in the chat, please, or try and come off mute and just shout at me. I would love that we can have this interactive. I'd much rather have it interactive rather than just sort of make it like a video that you could be watching on YouTube. So if there are questions or comments, please do shout them out. Also, if you want to download this presentation later on, I believe that tomorrow we'll be making it available on the relevant website. If you can't wait for that, it's already uploaded onto sbh4, and I've given you some instructions in the chat there as to how you can get to it. Right. So, just briefly, I mean, the presentation that I prepared for you is meant to be a reference document. There are 50 slides in it or more, and there's no way that in the next 50 minutes we're going to get through them all in detail. No way at all. So when you see the presentation deck, please don't, think that we're going to go through it all today. That's not going to happen. But what I've tried to do is pull together some, what I believe are very, very relevant references, case studies, projects, background information that you can then use to frame the very, very specific work that you'll be doing with regard to metrology and metrological standards. That's your area of expertise, not mine. That's the world that you live in. I live in a different world. And what I've tried to do with the presentation I've put together is give you some insights perhaps from, let's say, real world operational worlds, in which fuels are likely to make it, which ones are less likely to make it. Try to give you some insights that I think will provide some context and perhaps help you with some direction and, let's say, market validation for the work that you're doing today and other projects that you might consider doing in the future. Okay, so that's really the input that I'm trying to give you. Let's go through. Good. I don't know whether anybody of you actually participated in these polls, but I ran some polls on LinkedIn quite recently. And how accurate are they? Well, it really depends on, the knowledge levels of the people who've responded and whether they're just guessing or they have some expertise to offer. But I did actually find these two poll results, I say, quite meaningful, quite valid. And if you choose to use these in some of your presentations in the future or your research proposal justifications, you're more than welcome to do that, to explain why you've chosen to look at certain fuels, why you've chosen to look at certain projects. But the survey on the left is really, I think, showing quite a clear indication that whether it's biofuels or e-fuels, some kind of combustion is likely to be, the predominant form of maritime propulsion going forward, according to the 119 people that voted, right? So if we go nuclear, onboard CCS, even onboard CCS is combustion still, right? Onboard wind and solar. So to have a focus on, metrology requirements of liquid fuels, metrology requirements of emissions monitoring from those liquid fuels, I think remains completely and utterly relevant. Yep, we're not going to see the whole world go to wind and nuclear. And then on the right-hand side, if you drop into, let's say, some of those biofuels or some of those electrofuels, e-fuels, and try and understand where people believe the future might be going, I think there's a reasonably strong preference for, let's say, e-methanol and green ammonia. Whether or not we can differentiate between the 33% and the 26%, don't get too hung up on the accuracy of the poll. But it was 193 votes. But again, we don't really know who voted. But again, is it really going to be hydrogen? Not so many people think so. Is it going to be biodiesel as an HFO drop-in? Not so many people think so, right? Or is it going to be renewable LNG to replace fossil energy? Again, not so many people think so. So I think my understanding of AJOY's program focus is that really the focus is on methanol and ammonia. And again, I would say that is validated, that is supported by the kind of information that we got from this particular poll. And again, if you're proposing additional research projects in the future and you're trying to explain to people why you've got to focus on ammonia and not a focus on XYZ or something else, this kind of information I think can be helpful for you. This table really outlines a lot of specifically e-fuels, electrofuels. We're diving into the electrofuel space here now, not so much the biofuels, and explains some of the key attributes of things like hydrogen, methanol, green ammonia, DME, dimethyl ether, which is a methanol derivative, renewable natural gas. And then I've got synthetic aviation kerosene over there on the right-hand side. But for that, you could also say synthetic diesel, or basically a synthetic hydrocarbon fuel to replace HFO. And you can see across the various different characteristics why certain fuels might be more or less attractive than others. I mean, for example, I think we all know this, unfortunately, ammonia suffers a little bit from the issues related to toxicity. Hydrogen gas suffers massively from the very, very low volumetric energy density. In an aeroplane, this is what you want to worry about, the gravimetric energy density of the fuel plus its container. On a ship, or in a shoreside terminal, what's much more important is the volumetric energy density. And this is really one of the unbeatable characteristics of liquid hydrocarbon fuels. Look at the energy density up here, and we might say similar for heavy fuel oil. It's just completely and utterly unbeatable, which is, of course, why we've used HFO as a fuel on ships so much in the past. And trying to say, okay, well, let's use something else. It's really only LNG that has a similar energy density, but then the problem obviously becomes cryogenic storage. Yep, so people are beginning to look more at ammonia or methanol. Whether or not DME, dimethyl ether, whether or not that ever makes it into the scene, I don't really know. Again, what you do is you start with two methanols, you slam them together, you dehydrogenate, and then, of course, you've got DME, right? An improved energy density, but as you can see here, a lower hydrogen yield in its production, which is really very, very much related to the cost. And we need to trade the energy density off against that. So, yeah, should we be focusing on ammonia and methanol for a lot of our studies right now? I would say yes, that's entirely valid. If you were to go one step further, maybe in the future you would take a look at DME and also perhaps RNG, renewable natural gas. But again, that's not going to give you a different emissions profile to LNG as we have it today. Good. So let's take a look. Let's pick one of those off the list and start somewhere. Let's start with ammonia. I do believe that there will be a future for ammonia as a maritime fuel. That's a personal belief. Right? I think it will be limited to heavily industrial applications because of its toxicity. I think there's also a huge challenge to overcome with the Siemens Union because these are the people working on board the ship and down in the engine room who are most likely to be impacted by any toxic leaks. So it's not a slam dunk that ammonia as a maritime fuel will make it, in my opinion, but it does stand a high chance in some applications, especially industrial maritime applications. And that's where we're seeing it penetrating today. The large iron ore carriers, for example, moving between Australia and China. But once we start saying ammonia as a maritime fuel, we need to think, okay, am I going to burn it on a gas turbine? Gas turbines sometimes operate on, let's say, very, very modern ships, often military ships moving very, very fast. Is it going to be burnt on a two-stroke engine, a bit like a heavy fuel or diesel engine as we operate today? Or is it going to be used on a fuel cell, right? And the quality requirements of the ammonia as a fuel differ significantly between those different applications. So the metrology and measurement requirements of those three different, let's say, energy release forms will also differ significantly. Furthermore, the emissions profile from those different energy release forms also differ significantly. So when we say ammonia as a fuel, we need to go beyond that to think about the metrological requirements. Because ammonia as a fuel for fuel cell means I need a different quality and purity of ammonia. I need to process it in a different way, and I have different emissions. Ammonia for a two-stroke engine again means I need a different quality of ammonia coming in, metrological requirements of the fuel, its purity, and I'll have a different emissions footprint coming out in terms of emissions monitoring, and also different emissions mitigation in terms of DNOx. So the sensors, the metrological requirements are not just related to the fuel. They're a combination of the fuel and let's say, the powertrain system that I'm going to use to get the energy out of that fuel. And that then gives you a huge metrological challenge. It gives you a big matrix to draw, all the different fuels, all the different ways that they can be burnt or used, and really gives you quite a complex matrix of metrological requirements in terms of within the process and emissions monitoring. And I think, therefore, picking the projects that are going to be the most relevant to the future is quite challenging for you because there are so many different options. But again, hopefully with the presentation deck that you've got in front of you today, you'll begin to see maybe which of those options are most likely to prevail so that your research and your future metrological standards are most relevant to where the world is most likely to go. So yes, we are seeing specifically bulk carriers and large petroleum refined products, tankers, crude oil tankers moving towards ammonia-fired engines with a few vessels on order. In terms of how we use ammonia on a two-stroke engine, well, inevitably it will need a pilot fuel such as diesel, because the ammonia has such a high ignition energy. It just doesn't want to burn, is the truth of it. It burns with a lazy flame and it doesn't want to burn. So we need to ignite or detonate with diesel. And ultimately, in terms of the overall energy requirement, we're typically using about 5% diesel and 95% ammonia. And again, people need to be aware of this, that ammonia on a two-stroke engine is not a carbon-free fuel. It is 95% carbon-free because it needs to be mixed with diesel. And therefore also the emissions footprint and what you'll need to measure is a combination of the ammonia combustion and also a small amount of diesel. Mitigation in terms of scale and size, I mean, this is an SCR, a selective catalytic reduction unit from a maritime vessel. So, when we talk about scale and size of operations and emissions mitigation, let's not forget some of these big ships burn a lot of fuel and potentially create a lot of NOx emissions which need to be mitigated. Just wanted to throw that one in for you there. We're not talking about small DeNOx systems that you might put on the back end of a car or a truck. These are monsters. But talking about car and truck, I think we can lean on what has been done in cars and trucks with regard to ammonia emissions monitoring and process control and sensors to imagine how the world of maritime ammonia use might evolve. And here's really just a reminder that a truck ammonia DeNOx system based on diesel fuel is full of sensors. And in a large-scale environment, some of those sensors would need to be replaced with more accurate gas analyzers for emissions monitoring. Yep. So there's a lot of work to be done, a lot of metrology to be done around process control, feedstock purity measurement, which we don't measure in the truck, and also the emissions monitoring. Good. Let's stay with ammonia, and I'm now going to go through to look at cracked and partially cracked ammonia as a maritime fuel. What do we mean by cracked ammonia? Well, a lot of the time when people talk about ammonia cracking, they're talking about very, very large port-sized crackers. So moving large quantities of ammonia around the world from where it's cheap to make it to where it needs to be used in large quantities and cracked back to hydrogen and then perhaps put into a hydrogen pipeline. And on the left, we've got there a very, very large ammonia storage tank and the kinds of ships that will move large cargoes of ammonia around the world. And on the right, you've got two models of ammonia cracking. One here, a centralized model where it's cracked centrally and then perhaps the hydrogen is distributed. And a second model where the ammonia itself is distributed and then cracked, let's say, at the point of use. Either at a chemicals plant where they want to burn the hydrogen or a chemicals plant where they want to use the hydrogen, or on board a vehicle. I don't actually ever see that it's going to go on board buses. I'll be very, very clear. I also don't see that it's ever going to go into cars, but it could easily go into other vehicles and industrial applications. So what does an ammonia cracker look like? Well, they're all different, to be very honest. This is a particular example from Johnson Matthey. So I suppose this is going to be Honeywell UOP in the near future, if you've been following the news. But basically, the heat for the cracking is provided in this particular configuration by burning some of the ammonia. All right. There are other configurations and where the ammonia is cracked, and then some of the hydrogen at the back end is used to create the heat inside. But whether or not we're burning the ammonia or the hydrogen to create the heat, again, we have a metrological requirement here, or lots of metrological requirements, simply for ammonia cracking. Because this cracker burns a lot of material, whether it's ammonia or hydrogen, to create the heat. So we have a lot of flue gas emissions. So we have an emissions monitoring responsibility. And of course, there will be process control sensors and analyzers within the process to make sure that the cracking is happening well, that we've not got a lot of ammonia slip coming through the cracker, and various other key process parameters. Furthermore, the ammonia coming into the cracker is of critical importance because the cracker contains a catalyst which is very, very sensitive to certain poisons. So it will also be necessary up front of the cracker to be measuring for certain impurities such as sulfur compounds, which shouldn't be in the ammonia, but they might have entered the system through some failure upstream. So again, on the inlet, process control, emissions monitoring, and the hydrogen coming out of this system, there are metrological requirements throughout the ammonia cracking process. Some related to quality control, some related to process control, some related to environmental emissions monitoring. If we then think about ammonia cracking on board the ship or inside a truck or a train, it's very similar technology at much smaller scale. So this is an example of a maritime proposal, a two-stroke engine proposal, where we have our cracker here. And you might notice that this is partial cracking. Okay, so a lot of the ammonia bypasses the cracker and goes directly into the engine. And typically 10, 20, 30% of the ammonia would be cracked here. But clearly, if we're just burning the raw ammonia, we would have, the emissions issues that we had discussed previously. If I'm cracking 10 or 20% of the ammonia, I have additional process control sensors and measurement requirements inside of the cracking loop as well. Plus, don't forget that the ammonia can actually be going into the exhaust to provide denox afterwards. This is an example actually from an aviation turbine, but I would just remind you that some very fast ships in particular actually run gas turbines instead of two-stroke engines. It's less common, but especially in military applications, defense applications, high-speed ships, it is actually quite common to be running a gas turbine down there. So again, we might actually see ammonia going onto gas turbines on board ship. At these smaller scales, again, it could be quite large if it's a ship, but this cracker here has come straight out of a train where ammonia is being cracked to go onto a diesel locomotive engine. This is effectively what a small scale cracker could and would look like. This particular one is from a German company called Ammonergy. I don't know if there's anybody from Ammonergy on the call today, and if you are, hello. And really just to give you an idea of physical dimensions. We can also go a little bit, I say, further. We can crack the ammonia. We can then put the ammonia onto a fuel cell. This is not internal combustion. This is now a fuel cell, whether it's a high temperature fuel cell, solid oxide, or high temperature PEM, or low temperature PEM, whatever. But again, I really just want to point out to you that if we're coming away from a two-stroke engine or a gas turbine with those particular combustion profiles, coming into a fuel cell type operation, whether we crack or not, we're going to have a very, very different purity requirement coming into the fuel cell and a very, very different emissions footprint coming out of the fuel cell. Repeating what I said earlier on, it's not just the use of ammonia as a fuel that you need to consider for your metrological requirements. It's that matrix of which fuel and which, let's say, powertrain system, turbine, two-stroke, fuel cell, and even within fuel cells, there are all sorts of different dimensions. Again, this is a different fuel cell example. This is AMOG, not Ammonigi. This was Ammonigi, you see here. This is AMOG, different company, United States, Germany. And the AMOG idea is indeed to crack ammonia and then to create very, very high purity hydrogen, which would go onto a low temperature PEM fuel cell. And even within PEM fuel cells, you've got high temperature and low temperature with very, very different tolerances to impurities. So the metrological requirements or the purity measurement requirements coming into the fuel cell for PEM is a very high hydrogen purity. Coming into a high temperature fuel cell, much more relaxed. So again, even there, coming into a PEM fuel cell, there are two different types with two very, very different requirements on hydrogen purity coming into them. This is another onboard case. Actually, the ship wasn't powered by ammonia. This small utilities power generation system at the back was powered by ammonia. This is an H2 site ammonia cracker with integrated hydrogen membrane. But again, these kinds of systems, what's going to make it through to the end game, I think, is still very, very much open. But the more you understand about the types of systems that are being researched and proposed, the more relevant your research and metrological work that you're doing will become ready for the future and be much more future-proof. Here's again ammonia fuel cell systems. I mean, whether or not you know it, there are 8 of these vessels that were ordered for a Norwegian company, and they're being built in Vietnam. So, if people ask you, was that Fortescue Zero ship the first ammonia-powered ship? The answer is no. They might tell you it is, but it's not, and it wasn't. Good. Ammonia for power generation. So we're coming away from maritime applications now. We're staying with ammonia, but we're looking basically at power generation on land. Clearly, I think we're all quite aware, we need to, in the future, over time, burn less coal, burn less heavy fuel oil for power generation, move much more through to a renewable world. And the difficulty being, coal-fired power generation, base loader, relatively easy to manage supply and demand. Renewables, typically non-programmable and variable. So as we move through to a higher percentage of renewables in the grid, what we need to also add on is, let's say, power or energy storage that complements the duration of intermittence or variability. And when we think about power, electricity storage or energy storage, we really need to think about the storage capacity. How much are we trying to store? And also the discharge duration. Am I trying to discharge over a second, a minute, an hour, a day, week, month, or am I trying to get seasonal balancing? And there's a lot of technologies that we can do, for short timescales, small amounts, and a lithium-ion battery is fantastic, really good technology, very, very high round-trip efficiency. If we want to discharge for, let's say, 4 to 6 hours, brilliant. But if we want to store energy for a week, a month, or a year, then lithium-ion batteries are just absolutely useless. The business case completely and utterly fails. And we need really to think about molecular energy storage. So I talk here about underground hydrogen storage, underground gas storage, or we talk about conversion of the hydrogen to, let's say, ammonia or methanol. My point here being, when people talk about battery energy storage and say, well, that's going to be the thing, I'm kind of going, it's going to be one of the things. Yes, and it is brilliant. Round trip efficiency, unbeatable. But if we want longer discharge periods, we really do need to think about molecular energy storage. So I've just seen a question come into the chat. Hi, sbh4. My name's Steve, by the way. Have you taken LCA of different fuel pathways into account? Only blue-green makes business case. Okay. Have I taken LCA into account? I'm not presenting LCAs today. And you're expressing an opinion there, I believe. Only blue-green ammonia and MEOH makes business sense. If that's your opinion, that's absolutely great. Lovely to hear it. Thank you. Again, also, I'm not presenting business cases through today. But thank you for the comments. Here's a study that was done specifically for the UK. It was a General Electric and an IHI study. I mean, GE do turbines and IHI do burners. And this was really comparing liquid hydrogen versus ammonia supply chains, portside power generation, right? So this is a little bit similar to that cracking case that we looked at previously. The message of this particular study was that liquid hydrogen is less economically sensible or less economically viable than ammonia. Okay, so again, if you're trying to justify why you're looking at ammonia emissions and not other emissions cases in your meteorological projects, here's one good reference point to establish that. Again, I'm going to go through these slides very, very quickly. You don't need to sort of try and understand all of the numbers that are on these particular slides. You've got the slide decks, and also if you look here, the links through to the more detailed studies and analysis. So you can do a lot of research after the call today. When we think about the efficiency of ammonia-fired power generation, I think the benchmark is really going to be natural gas, so natural gas combined cycle, where we basically use the natural gas through a turbine to generate power. Then the steam that we generate is also going through a second steam turbine, so we get 2 hits of it, right? So we can get really, really high efficiencies on a combined cycle. If we go open cycle, we just get the first half. If we go combined cycle, we get the second half as well. And if that's the benchmark, because that's what we're doing today, natural gas, the question really is going to be, can ammonia deliver anything similar? And the answer is yes, we can get similar, in the sense that natural gas combined cycle sort of efficiency typically plateaus are out around 58%, and we can perhaps get as close as 59%, 56% using an ammonia fueled combined cycle, right? So if anybody's asking, can ammonia ever get close to natural gas in terms of process efficiency? I would say yes, we can get close to it with an intelligent cycle. And if you're running, let's say, natural gas open cycle, then we can beat that dramatically with ammonia on a combined cycle. So yeah, it really depends on the cycle efficiency. And again, here's another study. Again, you can take these studies out. The links are here, which is really comparing landed fuel costs versus levelized cost of electricity for ammonia, and trying to benchmark that versus various different options. Here you've got LNG, LNG plus CCS, direct ammonia, ammonia cracked to hydrogen, and liquid hydrogen. And you can see here really that the direct ammonia option is giving you an equivalent or very, very similar cost overlap, a lot of overlap with LNG plus CCS. Clearly, pure LNG is cheaper, but once you bolt on CCS behind the back end of the power generation, you're beginning to say that use of direct ammonia is less expensive, right? The question is, was it green ammonia, was it blue ammonia, etc., in terms of how it was produced? But we can see here that the economics of firing ammonia directly can be very, very good. Okay, ammonia cracked to hydrogen, we're getting a little bit of overlap with LNG and CCS, but it becomes a bit more difficult. If we simply burn the liquid hydrogen, the economics become quite difficult again, right? So these are some of the relevant things to consider when we're talking about ammonia to power. I also ran a question, a poll on my LinkedIn profile related to ammonia to power recently, and basically asked the question, will it ever be used? And if it is, how will it be used? And you can see the answers here, and yeah, there's a slight majority of people saying no, it won't, because of various different reasons. Either it's too expensive or the NOx emissions can't be resolved. But a good number of people basically saying yes, it will, and broad consensus that it would potentially be used on turbines and gensets. So gensets is basically 2-stroke engines. So again, these kinds of information I think can be quite relevant for you to think about what kind of meteorological projects you take forward. I've got another. Good. So that was basically ammonia for power generation. And I'm quickly going to look at some of these slides related to co-firing, because we don't need to fire pure ammonia. There was a lot of studies done in Japan, basically co-firing ammonia with diesel on a turbine, a microgas turbine, and you can see here some of the results there. My point very simply being, we go ammonia plus diesel, integrated fuel use, a bit like the diesel pilot on the ammonia 2-stroke engine on the ship. Again, the emissions profile now for you from a meteorological perspective is a mix of ammonia and hydrocarbons, a little bit more challenging, I would imagine. Also in Heikkinan in Japan, we've got co-firing of ammonia with coal. This pilot, has been running, I think, for quite a long time. And again, we've got now the old coal emissions footprint plus the ammonia emissions footprint. Oh, great. A lot of metrological challenges to work in there for you. And again, exactly how you take your studies and evaluations forward, I think, is really going to depend on where you believe and in which parts of the world you believe these various different combustion ideas will prevail. In terms of doing that ammonia co-firing, a lot of changes needed to be made to the burners. Nothing else really was changed, but specifically to the burners inside the combustion chamber to allow the ammonia co-firing. And, here's some charts that really blow your mind away when you think about what could happen if people really start doing ammonia co-firing on coal-fired power stations in the future. Even if it's just done in Japan and Korea, you look at a lot more ammonia requirement. 20 million tons of ammonia per year is the current total traded volume. Total volume is around about 100 million, but the traded merchant volume is 20. And then, of course, if you start doing it in China, then you've multiplied the current total ammonia demand around the world by 3. All right, so I've got another question here from Florian. Hello, Florian. Hello, Stephen. ... Could you please elaborate on the topic of NOx? Okay, good. Yeah, okay, good. Let's take a look at NOx. All right, okay. Let's take a look at NOx, right? Again, I'm going to go more into NOx on turbines rather than NOx on diesel. But I mean, ultimately, you'll still need to do DNOx if you're firing ammonia, just like you need to do DNOx if you're firing diesel. The good news about DNOx with ammonia fired is you've already got ammonia on board to do the SCR. All right, let's take a little bit of deep dive into our emissions monitoring. We're probably not going to have much time to look at methanol today. Poor old methanol, a bit unfair, but I just really want to give you a flavor of some of the information that I've got in the deck here. Let's go straight through into the emissions monitoring now. If you look at the ammonia combustion pathways, it's a nightmare. I don't know how many of you work with NOx and NOx systems, but the chemistry is just so completely and utterly insanely complicated. Well, at least that's what I think. You probably find it very easy. But, we can go through to NO, NO2, N2O, nitrogen. Oh, it just goes anywhere, right? And I think for me, the difference between the future and the past, when we start burning ammonia as a fuel, is in the past, we've often worried about NO and NO2, fine and fair, and we've bundled it together as NOx. And I think that's going to have to continue. No way that's going to stop. My concern is that we're also, if we're not careful, going to get N2O coming through, nitrous oxide. And if the whole reason for displacing a hydrocarbon fossil fuel with ammonia is to reduce greenhouse gas emissions and reduce CO2 emissions, if we substitute those for nitrous oxide emissions, then we've lost. Because nitrous oxide is around about 250 times more potent as a greenhouse gas emission than CO2 per kilogram, right? So if we end up with an ammonia-based combustion system with a lot of N2O emissions in it, we've lost, okay? And N2O, why would we end up with N2O? Well, basically, if there's not enough oxygen there, is fundamentally the answer. As soon as the oxygen comes there, then we can go through to higher oxides of nitrogen. But these reaction kinetics are pretty much instantaneous. These things don't happen slowly. This is all happening instantaneously within the combustion chamber. And we can see, through various different studies, and again, please download some of these references, if we partially crack the ammonia, then we end up basically with a flame speed and flame characteristics that look a lot more like methane. Yep. So we can, by partially cracking the ammonia, we can basically create combustion conditions that are much more similar to what we know a lot about methane or LNG. And what people have realized is that people sometimes call it lambda, or the reciprocal of lambda is the fuel air equivalence ratio, or theta. Is this theta? I'm not very good at my Greek characters. But basically, if we want to get the N2O, and please remember this is nitrous oxide now, N2O, not total NOx, not NO, and not NO, but N2O. Specifically, this is N2O. If we want to get the N2O down, then we need to be working in a relatively tight band of the of lambda, of the fuel air or the fuel oxygen ratio. And what that says to you is a couple of things. Number one, we can avoid, to a large extent, N2O emissions. Good news. We also need to control the engine combustion, the fuel-air mixture, in a relatively tight band, which means that the sensors and the metrological requirements to achieve that need to be pretty good. Rapid response, pretty accurate. Okay, so again, in terms of the metrological requirements, you're beginning immediately to see what kind of process control sensors the engine would need. And at the back end of the system, we're probably already measuring NO and NO2, combined NOx on a chemiluminescence analyzer, great. Who's going to measure the N2O to make sure that that is not coming through as well? That's going to need different emissions monitoring and measurement sensors and technology. So, what have people used in the past? Well, QCL, quantum cascade lasers, you people would know all about this much, much, much better than I do. But that's what was actually used in this particular paper to measure the N2O. And then we kind of say, all right, so where in the past have we actually looked for N2O measurements and international standards? There are some industries where the N2O emissions are incredibly high, typically making nitric acid fertilizer, for example, where we burn ammonia intentionally to make oxides of nitrogen. Listen, I don't actually really know whether those measurement protocols are going to be relevant to emissions monitoring because the nitrous oxide concentrations are so much different. But I'm sure you also know the CO2 N2O peaks broadly overlap in the IR spectrum. Listen, I'm trying to tell you things in a very, very naive way that I'm sure you know a lot about. But I'm really just trying to make the point, can we leverage existing metrological standards from other sectors into what we're trying to do with N2O emissions monitoring? I don't know. Do we understand some of the problems with regard to CO2 and nitrous oxide peaks overlapping, which is very, very relevant? We've got a blended hydrocarbon fuel plus the ammonia. How can we deal with those? How can we learn from the past to accelerate an effective system from the future? That's what I'm trying to get through to you here. So I can see another question coming through. Tobias Eriksson, hello Tobias. Hi Stephen, do you have any slide about analyzers for ammonia slip and nitrous oxide inside? Okay, good. Let's keep going and let's see if we do. So, how, again, I'm really addressing the point of N2O here because I believe that most people are quite familiar with how to measure NO and NO2. So I'm basically trying to say N2O. You've seen the quantum cascade laser. Here's another slide, which is basically looking at a Fuji CEMS using NDIR, so is that non-dispersive infrared? I think I said that right, did I? To look at the N2O and also the NOx, but basically look at them separately, different IR spectra, and also how you compensate for the CO2 peak overlapping with the N2O peak needs to be dealt with. And this is a classical, flue gas emissions monitoring system and setup, but I think there are certain aspects of this that can come directly into maritime emissions monitoring. We can also look at some, let's say, smaller units. This is a handheld, a portable unit that can be used, the kind of unit that a consultant might use to go around lots of different sites. So not continuous emissions monitoring systems, but let's say quarterly or annually schemes. And again, on board a ship, it might not be a continuous requirement that is needed. It might be once a month, once every 3 months, once every 6 months process validation. Yeah. But again, these are also using NDIR technology. So in answer to your question there, Tobias, NDIR seems to be I think a reasonably robust, cost-effective technology for looking at NO, NO2, NOx, and whether or not we can actually handle N2O on similar kind of equipment, I wouldn't really know. You'd have to go and talk to the manufacturer. N2O on FTIR, again, FTIR, whether it's going to survive on a ship, I'm not entirely sure. Ships tend to be high vibration, very, very unstable environments. FTIR really works incredibly well in the lab, but whether or not for validating certain standards or whatever, FTIR would be a good case, would really be the kinds of things that people like you should be trying to decide upon and make recommendations to the world about. But again, FTIR can be used very, very effectively, specifically for N2O and ammonia measurement. Okay, so let's zip. If there are any other questions, please do keep them coming in the chat. I appreciate I'm answering some of them and perhaps avoiding others, but please do keep the questions coming. Let's just quickly go through to methanol. Maybe we'll give it a bit of a chance. Methanol as a fuel is significantly more progressed than ammonia. I mean, this is a methanol tanker owned by Methanex, which is carrying a methanol cargo and also powered by methanol. And the Stena Germanica has been operating on methanol for several years. And if we look over here at the number of methanol-powered ships on order, it's significantly more than the number of ammonia-powered ships. And we could. It's imaginable to get to a situation where methanol is so far ahead of ammonia that ammonia just has no place anymore. It is conceivable. I'm not saying that will happen, but it is a conceivable way that the world will go. Around the world, we tend to like single technology solutions. They're easy to implement. The infrastructure gets built up around them. If we have a lot of multiple fuels, a lot of different solutions, the infrastructure gets very, very dilute, and therefore we build in cost. If you think of Google, right? We've converged to a single technology solution for search. Well, maybe it's going to be ChatGPT in the future. I don't really know. But single technology solutions, especially for expensive infrastructure, tend to be favored. And therefore, if methanol really gets a head start, maybe it's methanol all the way. And again, these examples here are methanol basically on a two-stroke engine, like a diesel engine. This example here is slightly different. This is methanol being cracked and then going into a high temperature PEM fuel cell. Now, high temperature PEM, as I mentioned before, is much more resilient to, let's say, impurities or non-hydrogen species coming into the fuel cell. Advent and others make HT-PEM fuel cells. Come away from maritime and talk about methanol on land for power generation. A lot of studies were done about 20 years ago related to the use of methanol for power generation, because the idea was to go from natural gas to methanol and then burn the methanol. When people realized that LNG could do the job for them, the case for methanol decreased. When the gas crude price spread moved in favor of crude, again, the need for this particular technology decreased. But there has been a lot of work done and forgotten about methanol for power generation. Okay, and again, you can go through to some of these older research papers and learn a lot about it to understand what the emissions footprint would be, what the efficiencies would be, whether or not it ever stands a chance of coming back into the world and displacing or competing with ammonia, with renewables, with anything else that you might choose to mention. Okay, there's some really, really useful input from Marcus Haas. Thank you very much indeed for that insight, Marcus, and I hope everybody's got their eyes on the chat. Endresenhauser, SICK GmbH, has class-approved analyzer to measure NO2 ammonia as well. Okay, fantastic. That's exactly the kind of information that's really, really good to get you sharing amongst yourselves. Thank you for that input, please, Marcus. Here's another case study. This is firing methanol on what I refer to as a gas engine, or a two-stroke type engine, with a lot of benefits in terms of reduced particulate emissions, reduced rubber. This was done by Dor in Israel. But really, I mean, if you read this kind of information, you'd go, why would I use anything other than methanol? So yeah, please again, look at what's been done, look at some of these references that I'm giving you to leverage the past in terms of directing your research in the future. Coming back to fuel cells, this is a direct methanol fuel cell, DMFC, very, very suitable at very, very small scale. Begins to get uneconomical at larger scale because you need so many precious metals in the membrane. If you go larger scale, you really want to put hydrogen onto your fuel cell. If you stay small scale, then you can go direct methanol. But again, something like this, you'd want to be able to measure the purity of the methanol. So you'd want to validate the purity of the methanol through the supply chain. Emissions profile coming off something like this, relatively benign, you would hope. But I'm really just wanting to underline what I said before. It's not just about the fuels, it's also about the powertrain. And that's really going to determine the metrological requirements coming into and out of the system. Sequence, this is again high temperature PEM, similar to what we looked at for Advent. Again, much more tolerant of impurities coming into the fuel cell. Let's go upstream now. We've talked a lot about utilization of methanol or ammonia, so how it's burnt or used on board a ship or on board land to make power. Let's go upstream and ask ourselves, well, what about the meteorological requirements as these new fuels are being made? And we're making e-methanol, synthetic methanol from green electricity in Kasso in Denmark today. This photograph is about a year old from when the site was under construction. These are the Siemens ELISA PEM electrolyzers that are in these various different houses here. This facility is now up and running. So as you build a new methanol production facility such as this, of course, there are process control requirements on site to make sure that the process is well managed, the product quality is under control, and if there are indeed any emissions from the site, which there are, they are also monitored. They'll be very, very similar, frankly speaking, to the way an old methanol process has been operated in terms of process control requirements around the methanol synthesis loop, what needs to be measured, the concentration that it needs to be measured. So I don't see massive differences in the metrological requirements as we transition here. Similar, a lot of cases in the China for using what's referred to as recycled carbon. So this is not biogenic CO2 and green hydrogen. This is CO2 that's been captured from an industrial process, probably a petrochemical process such as ethylene oxide production, where the CO2 is not biogenic, it's recycled fossil CO2. But again, doing something like that means that we use the carbon twice before it gets emitted. So there is a CO2 emissions reduction. But again, I don't really see the metrological requirements as we shift that particular methanol production technology being particularly different to what we would have needed in the past. So there we go. We've looked at utilization on board ship. We've looked at utilization for land-based power generation, and we've looked at various different powertrain systems, burning it, turbines, fuel cells. We've looked at the process control and emissions-related meteorological requirements, and then we went upstream to ask whether or not a lot is going to change as these new fuels are produced. And my answer on that last one is no, but my answer on the utilization points is absolutely. And it's much more complicated than just asking which fuel, whether it's methanol or ammonia. You really need to dive into each particular powertrain in the combustion system. Pure ammonia combustion, ammonia plus diesel, cracked ammonia, etc. And as I've said previously, I think for me, one of the main concerns that we get our heads around going forward is N2O, and the risk of N2O emissions being a new risk in comparison to what we might have confronted in the past using, let's say, hydrocarbon fuels and then selective catalytic reduction. So I can see that AJoy is joining us again. I'm going to be quiet now and say thank you very much indeed for your attention. Thanks for the questions. I'm glad I could answer some of them. Sorry that I didn't answer them all.